here. All right, guys, just a quick recap of what we learned last week, guys. Basically, we talked about how magnetic fields are going to behave, right? The key point here was that magnetic fields are always going to go from north to south, yeah, guys. Very, very important. And the reason why they attract is because the magnetic fields connect. And the reason why they repel is because the magnetic fields cannot connect, right? Then after that, we also learned about the term ferrous and non-ferrous. Ferrous and non-ferrous is basically magnetic and non-magnetic materials. Not all metals are going to be magnetic materials. Always remember that. We also talked about induced magnetism. Induced magnetism is to create magnetism onto this iron bar here. And the key thing here is that the immediate opposite of the iron bar will be the opposite pole. Meaning to say, if I swipe it towards the right here, you can see that the immediate opposite is going to be a south pole here as well, guys. This is what we call induced magnetism. Then after that, I also talked about this part here. Very important, guys. The difference between permanent and temporary magnets is just that one is made of steel and one is made of iron. Hard to magnetize, hard to demagnetize for steel. That's why they retain their magnetism over a long period of time. Whereas for iron, it's easy to magnetize and easy to demagnetize. So they do not retain their magnetism. I also talked about this one here. This here is basically the induction of magnetism onto an iron bar with coils, right? So basically what happens is as soon as there is current flowing here, draw this up. As soon as there is current flowing here, what happens is there will be magnetic field, right? And this magnetic field will actually induce magnetism onto this iron bar, and this iron bar will become a stronger magnet than just the coils itself, because simply the fact that there are a lot of magnetic field lines interacting with the iron bar here, a lot of magnetic field lines, right? And after that, we also talked about the characteristics of the magnetic field. Key word here is that the weaker magnets have less magnetic field and the stronger magnets has denser magnetic fields. And we also talked about magnetic field lines never ever intersecting each other. Very, very important, right? Then finally, the second last part, we talked about this part here also. This part here is important, guys. You're basically using two things to prove the what's it called, the pattern and direction of the magnetic field. The iron filing is the one that is going to allow you to show the pattern of the magnetic field, and the compasses will be the one that shows you the direction of the magnetic field. Very, very, very important. And finally, this part here, I've mentioned this part here, you must know what's going on, because later on in the following few chapters, when they talk about AC and DC, you're going to need to know this. You need to understand that when there is current flowing in the conductor here, it will generate its own magnetic field. And this magnetic field's direction can be induced using the right-hand grip rule, whereas your thumb is supposed to be your current and your four fingers are supposed to be the magnetic field. I also talked about the final part here, where X and dot, guys. X means to say buried treasure, right? You're supposed to dig in, right? So the current is going into the paper, whereas dot means to say current is coming out of the paper. So using a right-hand grip rule, you'll find that the magnetic field will be clockwise here. It will be anti-clockwise here. Very, very important. And this one is very, very important. Always comes out in your exam one, right? Then after that, I asked you all to attempt the questions here, and then we were supposed to discuss this, guys. Let's go through each and every one of the questions one by one, guys. If you look at the first question here, which statement about a magnet is correct? Magnets attract a gold rod? Not really. Magnets does not attract plastic rods? Most likely. A magnet never repels another magnet? Nope. A magnet repels another unmagnetized? Nope. Okay, so the obvious answer here is going to be B lah. All right. Then after that, a student wishes to make a permanent magnet. She has an iron rod and a steel rod. Which one is it going to be, right? Type of material. If you want to make permanent magnet, must be steel. And the reason why we use steel is because it's considered a hard metal. It's hard to magnetize and hard to demagnetize, retaining its magnetism. So second question is definitely going to be C. Hey, stop me if you have any question, guys. I'm assuming that you all did this already. Oh, now I realize that there's a same repeated question here. Jesus. Anyways, two nickel bars are placed close to the end pole of a bar magnet. The nickel bars become magnetized. right? So this is the nickel bar and it becomes magnetized. Immediately the opposite here is going to be the south. Means to say here will be north. And if this is north, this north will induce magnetism onto this, and this will be south yet again, and this will yet again be north, right? So from here they ask you, what's going to be P and Q? P will be N and S. So these two is confirmed wrong already, right? And the forces between them definitely going to attract, right? Because, like I said again, only magnets and magnets can repel, guys. I mentioned this last week also. If I want to test this side is really a north pole, I need to bring another magnet with a north pole here. And then if they repel, only I know that they are really north poles. Quick user interface. How do I disable this thing? Does anyone know? I've been trying to Google on how to disable these descriptions. For some reason, it keeps coming up. So annoying. Anyone knows how do I disable this stupid yellow box here? Weird. Okay. Anyways, same thing. Permanent magnet, definitely steel because it's hard. So it's C. Nothing much to explain here, guys. Anyone has any questions for first 4 questions or not? Should be relatively straightforward, I assume at least. Right. Then after that, moving on to this next page here, which statement about magnetism is correct? An unmagnetized iron bar becomes magnetized when it's placed near a magnet. Unmagnetized iron bar becomes, okay, looks logical. An unmagnetized steel bar can be magnetized by passing a current through it. Nope, you need large current. Direction of magnetic field lines is from north to south to north. Nope. The end poles of 2 magnets attract. Definite. No. So the answer here can be no other than A. Logically thinking, right? In which pair are both materials magnetic? Aluminium, straight away no already. Copper, straight away no. Iron and steel, most likely. Aluminium, no. Guys, if you have a hard time remembering which one is the magnetic materials, please refer to the diagram on the first page, guys. You know, the table where it shows ferrous and non-ferrous. Iron and steel are always the most common ones. Then looking at this example here, the diagram shows the magnetic field line around 2 bar magnets. You can see that the magnetic fields are coming out here, indicating this is obviously a north and north, right? So anything other than north and north is not logical, right? I think one of you guys got this question wrong, right? When we were doing the ABC in the Google Sheets. Make sure you read the magnetic field lines, then from there you should know that it's going to be north and north. So it should be C, right? Then the next page here, this one I taught you guys how to do it already, guys. This current here, you're supposed to find the magnetic field using a right-hand grip rule, which is going to generate an anti-clockwise magnetic field. The anti-clockwise magnetic field means to say by right, the compasses should be pointing in these directions, but only C is the one that is aligned, guys. So this question here, your C should be the answer, because the magnetic field here is going to influence the weaker magnet here, right? Then after that, I ask you which are only non-ferrous metals, aluminium, brass, and iron. Nope. As soon as I see the word iron, no. Is there another iron? No. It says C as steel, no. So obviously B is the answer, right? Brass, copper, and lead. These are all the non-ferrous, which are the non-magnetic materials. Are very important, right? Then after that, this one here, this one is actually one of my favorites because I realized that especially the Chinese educated students, they'll always get this wrong. It says that an electromagnet with a soft iron core is connected to a battery and can open a switch. The soft iron core is just above some small soft iron nails, right? The switch is now closed. Closed means to say it's like this. Left closed for a few seconds and then open. What do the soft iron nails do as the switch is closed, and what do they do when the switch is open? A lot of these students, you know why students will get this wrong? Because they are directly translating close as guan, right? Guan as in offer. I mean, everyone is Chinese here, right? I assume, I assume everyone here knows Chinese, right? Then what's going to happen is they think that, oh, closed is guan, as in like off, right? Then they think that, oh, when this is off, then obviously the nails are going to jump down, right? Stay down, right? But in reality, in English, close means to say the circuit is closed like this. Means to say the current can flow here. And when there is current flowing here, obviously, good Indian Shut up, like Kuning. Never mind. Okay, anyways, coming back here. When the switch is closed, obviously the nails are going to jump up because as soon as the current flows here, it will magnetize this soft iron core here and cause it to attract. And then the switch is open, obviously the nails are going to fall down. So A is the definite answer here, guys. A is the definite answer here. Anyone's got any questions for this part before I move on? Anyone? Didn't get anything from this page here? Good, 100%, just what I like. And then we move on to the paper 4 questions here. This is one of the interesting question here. It says that a physics teacher suspends 2 pointers in a magnetic field. There's 2 pointers in the magnetic field. One pointer is made of brass and the one is made of magnet. Okay, this one is the brass, this one is the magnet here. She holds the pointer in the initial position shown in the 2 upper circles in figure 7.1. She then releases the pointers. In the lower circle of figure 7.1, draw the settled final position for the 2 pointers here. It's so annoying. How to disable? Okay, nice. Okay, so first and foremost, let's ask a random person today, shall we? What do you think is going to happen to the brass pointer when you place it in a magnetic field? And look who pops up at first. Hannah, tell me, what do you think will happen when I place this brass pointer in these strong magnetic fields? Hannah, what do you think is going to happen? Good, but you're not Hannah, Jerry. Yes, definitely is nothing is going to happen. Why? Why is there nothing going to happen? Because brass is a non-ferrous material, right? Meaning to say, even if you put it in the world's, even if you put it in the world's, even if you put it in the world's strongest magnetic field, guys, you would have no effect on it. Meaning to say, the brass pointers will still be in a horizontal position. But today, if you have a magnet here and you put it in a strong pole, tell me, Jen Lim, what's going to happen to this, what's it called, compass or whatever this thing is? Where will it point? N on top. Good. You'll have your N on top and your south at the bottom. Now, there's 2 ways to look at this answer, guys. Why will the N be on top? Is because, number 1, this is a stronger magnetic field, right? If this is the stronger magnetic field, these weaker magnets will always follow the direction of the stronger magnetic field, right? So obviously, it's going to go align like that, how the compass aligns with the magnetic field, right? The second way you can think about it is, if my magnetic field is going upwards like this, right, then obviously my bottom is a strong north, right? Only then can my magnetic field go upwards, right? And at the top is a strong south, right? Then if I have a compass here, obviously this north will be attracted to this south and this south will be attracted to this north here, right? So you're supposed to draw a vertical position of the compass, guys. The north will be pointing on top and the south will be pointing at the bottom, right? And this is exactly why you need to start explaining or explain the final position of the brass pointer here. You're going to say, brass is a non-ferrous metal. It will not be affected by magnetic field. And your final position of your magnet, you're going to say, weaker magnets will align to the position, to the direction of a stronger magnetic field. This is your 2 answers that is going to give you your 2 marks here. Description automatically generated. How to remove this? How to remove disable permanently. Then after that, finally, they ask you to suggest a material from which the magnet is made of. It can be no other than steel because it must be a permanent magnet, right? Permanent magnets are always made of steel, guys. Okay, and that concludes the first question here. Anyone has any questions for this part or not? To demagnetize hard metals like steel? Okay, good. That's a very good question. The demagnetization process are usually there are three. Number one, you either heat it up with very hot fire. Or number two, you hammer it down. Or number three, you supply it with AC current. But for some reason, they actually removed this from your syllabus already, guys. If you check the syllabus here, you are not required to know how to demagnetize all these hard metals anymore, right? But last year they were still in the syllabus. They removed it this year. So these are the three ways theoretically to remove the magnetism from a magnet. But I have tried this as my favorite method. What I did was I took a magnet, right, and I smashed it to the ground. I smashed it in the ground so hard it broke into 1,000 pieces. But the funny thing was it still retained its magnetism. And how do I know it retained its magnetism? Because as I picked up the thousands of pieces of magnets on the ground, they all still stuck to each other, right? So this one here, all these things are good in theory only. I think in reality, there's always going to be more than one factor that could affect whether it will magnetize or demagnetize. But yet again, it's out of the syllabus. You don't need to know this anymore. Okay. Okay, anyways, moving on to this next part here. This next part is a bit of a theory concept kind of scenario, guys. If you look at this question here, what do they want from you? Figure 8.1 shows a vertical current carrying wire passing through a point at X here. On figure 8.1, sketch on the card the pattern of the magnetic field produced by the current in the wire, right? So they're asking you to draw the magnetic field from the current in the wire, right? And looking at the scenario here, since the current is going into the page, your magnetic field generated will be, Kunling, will it be clockwise or anti-clockwise? Will your magnetic field generated be clockwise or anti-clockwise due to this current here? Clockwise, good, excellent. Using your right hand grip rule, you would have attained that your magnetic field will be in the clockwise direction, right? And when you draw these magnetic field, guys, you are required to draw at least three of it. At least three of it, as you can see from the mark scheme here, at least three complete circles, right? Spacing is greater as the radius increases. At least one arrow to show that it is a clockwise direction, right? No contradictions. Meaning to say, you can't draw like one that is towards the right and then one towards the left and then one towards the right. I mean, it's psychotic, right? Obviously. So these are our criteria, and bam, 3 marks. Easy. Easiest 3 marks of your life. Just drawing 3 circles, right? Then this next part here, using your knowledge of investigating the magnetic field around the bar magnet, suggest an experiment or experiments to confirm that you have drawn the correct pattern, right? So this whole thing here is 4 marks, right? Is basically testing you. They're asking you to show how you know that the magnetic field is going to be in this circular motion here, right? And if I want to test the pattern and direction of the magnetic field, What are the two things I use again, Scott? Right-hand grip rule. No, the right-hand grip rule shows you the direction of the. Okay, I know. Okay, let me rephrase my question again. Today, right, I say that if the current is going downwards like this, according to my right-hand grip rule, the magnetic field should be clockwise now, right? But there must be another way to prove that the magnetic field is really going to be in the clockwise direction, right? What are the two things that I use to show the pattern and direction of the magnetic field? Using a compass, not just a compass, I'm using compasses because you need to align it here, right? And what do I need? What else do I need? What's that thing called? Compasses is to show the direction of the magnetic field. But before that, the I don't know the name. What's it called? Anyone can tell me what's that thing called or not to show the pattern of the magnetic field? What's it called? Iron what? Yes, iron filing. Very good. Right. Scott, remember or not, you're supposed to sprinkle iron filing onto this thing here first, right? And then iron filing will all align into the magnetic field. Then after that, you place the compasses here to determine the direction of the magnetic field. Remember or not, right? And this is exactly what you're supposed to write. This whole part here is basically just rewriting this in your own words. Is everything here? Everything that you see here. Everything that you see here is going to be answered. Hey, boys and girls, just rewrite everything down. Rewrite everything down, preferably with your own words, right? And then you'll get your 4 marks rating. Right, let me just show you what the mark scheme wants. What? Okay. Use compass. Observe needle, observe. Sprinkle iron filing, tap the paper, tap the card, align. Then after that, use compass to show the direction. Right. I keep emphasizing this, guys. Your iron filing is just going to show you the pattern of the magnetic field. You need the compass to show the direction of the magnetic field, guys. Very, very, very important. Please remember this. Right. So use your own notes. Basically everything that I've mentioned on top already. Okay. And after that, this part here is where it gets interesting. It says that the second current carrying wire is inserted vertically through the cut at Y. Okay, so there's another wire. I don't know whether it's up or down. It doesn't really matter. It says inserted vertically to Y here, right? So just why now there is a force on the wire of X. Right now, why will there be a force on the wire? Either it will go this direction or it will go this direction here. Why do you think this is so? Shamin, tell me, what do you write for this part here? Huh? You don't know. Nani? What about Tavish? Tavish, what do you think is the reason why there is right now a force on the wire X here? Why will there be a force when I insert another wire into here? Why will there be a force acting on this wire here right now? What's happening? What is generating that force? Anyone did this question? I'd like to see your answer and see if anyone got it right. Why, when I insert a wire at Y, Oh. Okay, interesting. Because it cuts the magnetic field lines. What cuts the magnetic field lines? No, no, no. Okay, guys, listen up. This is the reason why, guys. Hey, wait a minute. Oh, Junhao isn't here, right, today? Yeah. Okay, guys, listen up. Think about this really fundamentally, guys. Today, if, right, I insert another wire that has current flowing in Y here, what's going to happen is it will generate its own magnetic field, right? Let's just say like if the current is going downwards as well, the magnetic field generated by this wire Y would have a magnetic field like this, right? Do you see that the magnetic fields right now are actually interacting? The blue magnetic field lines are actually interacting with the red magnetic field lines, as you can see here. And when the magnetic field lines are interacting, they could either produce a pull or a push effect, right? In this case here, it will be a pull effect because the magnetic field lines are connecting, right? And then they become a stronger big magnetic field here, right? Guys, and this is your reasoning behind it, guys. You're supposed to say that magnetic field produced by current in Y is interacting with the magnetic field produced by current in wire X. You're supposed to say something like this, guys. You need to understand that when there is current flowing at Y, it will generate its own magnetic field, and that magnetic field will interact with the magnetic field from X itself. And this is why they produce a force. It's basically either attraction or repulsion force, depending on the direction of the current. Anyone don't know what I'm talking about for this part here? Anyone wants me to repeat this one? It's very important. The concept of the magnetic field lines interacting will always be tested in your exam. Okay. And then finally, the wire Y is moved to wire Z. It still carries the same current. Pick the appropriate box to indicate whether the force on the wire X is now smaller, greater, or the same. Which one do you think is going to be? Hannah, which one do you think is going to be? Do you think it will be smaller, greater, or the same? And tell me why. Slay. Where's the slay option here? Nani? Nani? Smaller. Why? Yes, it's because they are further apart. Guys, right now, they say that this wire Y is right now moved to wire Z here. It's moved to Z here. And if it's Z here, the magnetic field line will look something like this, right? It will still interact, but obviously it will interact much less compared to when it was at Y, right? And because the magnetic field lines interact much less, it will have a much smaller force here. Do you guys understand what I'm talking about now? Hey, good. All right. All right, all right, all right. Okay, now let's move on. Slay your hate and slay. Okay. Anyways, yeah, this concludes the exercise for this magnetic chapter. Very easy and simple chapter. Anyone's got any questions or not with the exercises so far before I move on to the next chapter, guys? Wow, welcome in. You missed the whole exercise part, but we are just about to move on to the new chapter already. So just watch the recording for the exercise part, which I hope you have done the exercises for. Okay, anyways, there's no questions. 100%, just what I like. If there's no questions, let's move on to one of the relatively similar concepts, which is what we call electric charges. Guys, you've definitely experienced electric charges or static electricity before. The most common example of static electricity is when you and your friend walk around in a shopping mall and then somehow your forearms touch, not in a gay way, right? Accidentally touch each other. Then you feel that electrical shock. You feel the electrical shock in between you guys. The reason why there is an electrical shock, if I were to illustrate it very poorly, right? Let's imagine this is you, right? And this is your friend. Okay, this is your friend. Somehow, when you're walking in a shopping mall, maybe because of the crowd squeezing you guys together, or maybe you guys just want to touch hands for a while, a little bit, right? What's happening here is, right, you eventually feel a very small, tiny electric shock here as soon as your hands touch, especially in the colder regions. Why this is happening is because there is a transference of electrons from one person to the other, guys. Meaning to say, assuming person A here, right, is more positively charged, right? Maybe it's like positively charged here. You still have negative charges, by the way, but it's just relatively more positive charge. And this guy here is relatively more negatively charged. So it's like he's still got positive as well, just that he has one extra negative charge here. What's going to happen is everything in the world will always try to neutralize itself, guys. And through the neutralization process, right, what happens is if today I have one extra electron here, I will try to neutralize. As soon as you guys touch, I'll try to donate the electrons away. This what's it called, the phenomena of the small electric shock is basically just a very small version of a thunder strike, guys. More negative charge person. Nani? Kunling, is that relevant? You bloody racist fool. Anyways, yeah. For those who are wondering how a thunder strike works, guys, you know what happens, right? The clouds above, because they keep constantly have friction against the air, it will actually build up charges in the clouds. These usually negative charges, right? And as soon as the thunder detects that there is something relatively more positive, right? A relatively more positive thing, right? What's going to happen is it will try to neutralize itself and pass on the electric current or electrons to the other person, thus resulting in a thunder shock, guys. Usually, if you're struck by thunder or lightning, right, you usually die. But I've seen some people that actually survive a thunder strike before. Miraculously, you can actually Google a little bit, and then they get this really cool tattoo-looking things to indicate that they have survived the thunder shock, right? But anyways, that's not relevant. Looking back into here, guys, the reason why there is thunder shocks and electric surges or like some form of small static charges is because of things known as electric charges, guys. There are only two known charges in the world. They are either positively charged or they are negatively charged here, right? It's very similar to magnetic field lines. The positive charge is like a north and the negative charge is like a south. But instead of having magnetic field, they will have electric field instead, guys. These arrows here are not magnetic field, they are electric field. One very interesting way to remember this, I remember this all the way since my high school until now. My teacher once told me that In order to remember the magnetic field lines, sorry, in order to remember the electric field lines, which one goes out and which one goes in, right? You always associate the positive charge to positive places. When I say positive places, I mean the so-called positive places are air quote positive places is like the school lah, the temple lah, the mosque lah, the church lah, the libraries, right? All these positive, air quote, positive places, right? Without anyone teaching you, you will automatically learn one day to leave these places on, right? Whereas the negative charges you can associate with the so-called bad places, negative places, right? And the so-called negative places are usually like the cyber cafes lah, the bars lah, the clubs lah, or the more the badder the badder places, right? Without anyone teaching you, automatically one day you'll find yourself going to these nightclubs, cyber cafes, or clubs on your own, right? So this is one way to remember it, guys. Tuition is definitely here, I would say. It has definitely more positives than negatives. That's why usually people will find their way to escape it, right? Stop coping. Stop coping. What do you mean? Anyways, right? Yeah. So this is one interesting way to remember it, guys. The positive places automatically, according to physics, will be going out, and the negative places automatically will go in. So it's just the physics of life, right? Yes. I guess we can't stop these young teenagers from drinking themselves to death. Just joking. Don't ever drink to yourself to death. There's always a limit to alcohol. Anyways, yeah, moving on. This is essentially what you're supposed to know, guys. The positive charges will have electric field lines radiating outwards, whereas negative charges will have electric field lines radiating inwards. And very similar to magnetic fields, if I place them both close together, you'll see that they are able to connect, and thus they will attract each other. Or like this one here, if they are both positive charges, you'll see that they are unable to connect, and thus they repel each other. Hey guys, the booklet I sent you, right? Does it have this picture inside already? Anyone can tell me if this picture is inside already? Jesus Christ, am I talking to the wall here? Can anyone tell me if it's already in your book or not? No, it's not. Oh, okay. Can you just copy this down real quick? Just sketch it out, guys. Don't waste too much time here because I want to try to finish as much as I can today. Not a lot. Very simple chapter as well. Okay. Can I copy this down real quick? I'll give you guys a maximum of 2 minutes to sketch it. Don't need to draw a perfect Picasso drawing. Okay, I will assume everyone is done. Yeah. Okay, for those who are not done, take a screenshot and do it yourself. Ding. Bottom drawings. What do you mean? This one? Or was it Kunling's drawing you were referring to? Okay, so if you look at the statements here, very straightforward, guys. Electric field is a region in which electric charge experiences a force. Guys, let me explain this a little bit. You will encounter this in your exam, and you actually need to write this down. And it's hard to memorize without understanding what's going on first, guys. You know, I say that the electric field lines are always going from positive to negative, right? In reality, unlike magnetic field lines, electric field don't exist one, There's no such thing as electric field. So how did the scientists come up with all this so-called electric field? Is by placing a small, tiny positive charge, and he observed which direction this positive charge was going. Obviously, because the same charges are going to repel, right? So if I place another one here, it will repel like this, place another one here, repel like this, place another one, repel, right? This gives rise to electric field. Same for this one as well. Today, if I have a positive charge here, because positive and negative are obviously going to attract, right? That's why it goes in like this, goes in like this, goes in like this, goes in like this. Guys, the key conclusion here is that there's no such thing as electric field. Electric field is a made-up thing by observing how this small positive charge behave in this relatively bigger positive charge, which gives reasoning to this explanation here. Electric field is a region which an electric charge, which is actually the positive charge, experiences a force. Oi, bloody hell, Kunling. Pay attention or not, idiot. Later you don't know how to answer this, I'll beat you, I tell you, one way or another. Okay, so this is your explanation. In your exam, they'll like to ask you how define what an electric field is, and you actually need to write this down, or you need to write it down in your own words. A region where a positive charge experiences a force or something along these lines, guys, very, very important. All right, then after that, direction of electric field at a point is the direction of the force on the positive charge at that point. Charges are actually measured in coulombs. The next chapter, we're going to learn to do the calculations. Obviously, the like charges are going to repel and the unlike charges are going to attract, unless Kunling is in the picture, right? As mentioned last week. So, by right, last week you said differently, right, for the north and the north, but whatever, right? So from here, the positive and negative charges are going to attract, and the negative and positive charges are going to repel each other. Unless it's from Zhenling. So this is Kunling, and this is, this is Zhenling, but they attract. What does fanboy mean? Let me Google that. Fanboy. Fanboy, a male whose appearance, behaviors, traits, and regardless. Shut up, lah. I see. So this is what a fanboy is it? Interesting. That's a bit gay, I must say. What the fuck? Okay. Nice. Okay. Yeah, definitely. Somehow. All right, whatever. Anyways, yeah. Moving on. Okay, this is going to be the second last part here. In order to understand how this gold leaf electroscope works, I need to let you understand how the charges are going to work as well, guys. Like I mentioned just now, guys. Pay attention. Stop talking about all this nonsense. Pay attention, guys. As all things in the world will try to go neutral, if today I have something that is relatively more positive charge or something that is relatively more negatively charged, it will try to neutralize itself as well. Let's imagine today, right, I have a metal brick here, right? It has positive, negative, positive, negative, positive, negative, positive, and negative here, right? This metal brick here is what we call neutrally charged. Today, if I want this thing here to become charged up, it doesn't matter if it's positively charged or negatively charged. If I want to make this thing charged up, there's only two methods. Either number one, I supply it with more electrons, right? If I supply it with more electrons, obviously what's going to happen is it will become negatively charged. Or alternatively, I could withdraw with electrons from it, meaning to say I can make these electrons go away through this earth wire here. If all these electrons were to escape through this earth wire here, then because there is a lack of electrons, then what's going to happen is this thing will become positively charged. Guys, one thing that you must note here is that only negative charges are free to move about, guys. Only negative charges are free to move about, and that is why they call it free moving electrons, right? Today, in order to understand this electroscope here, guys, let me just show you a quick video of how electroscope works. Everyone, pay attention to this video for 3 minutes, guys. I'll explain it one by one, parts by parts later on. Share sound.
Gold leaf electroscope. Gold leaf electroscope is an instrument that is used for detecting the presence of electric charge and its polarity. The instrument is also used for measuring the potential difference. The important part of the gold leaf electroscope are shown in the picture. The two extremely thin gold leaves are attached to the lower end.
Don't forget to clear search history after if other PC are. No, I'm not afraid.
Pay attention. In a glass jar through an insulating cork of rubber. A circular metal disc is fixed to the upper end of the brass rod. The gold leaves are extremely thin conducting foils that have low mass per unit area and are flexible, so they respond very quickly to small electrostatic forces.
We emphasize what he mentioned. She said that these gold leaves are very, very light, which is essentially the most important thing here, because the only thing that is going to cause these gold leaves to repel upwards or attract back inwards is because of the charges itself. So the first condition is this gold leaf must be very, very light.
Charging an electroscope by conduction. Let us see how an electroscope is charged by conduction. Charging by conduction involves the contact of a charged object to a neutral object. Here we can see a glass rod and a silk cloth. Now, when a glass rod is rubbed with a silk cloth, then the glass rod becomes positively charged.
This glass rod can become positively charged because all of its electrons was donated to the cloth, guys. Very important fact also. Take note on this.
Touch the positively charged glass rod with the metallic disc. What do you observe?
So this part here is important, guys. As soon as I take this positively charged rod, right, and I touch it to this metal plate here, you'll notice that this whole thing starts to become positively charged. Why will it become positively charged? Is because all the normal electrons here, like I mentioned, initially this thing was neutral. Initially it has negative charges, but as soon as I touch it, right, because this metal plate here detects that this thing is more positively charged. So what's going to happen is all the negative charges are actually going to be siphoned upwards and towards this rod here, right? Meaning to say this rod has stole all the electrons, leaving behind only the positive charge here. And because this thing is positively charged right now, the gold leaves will actually repel each other, okay?
Observe that as soon as the positively charged glass rod is brought in contact with the neutral metal disc, the gold leaves diverge due to the presence of similar positive charges on them. Now, remove the glass rod. We notice that the leaves still remain diverged. This shows that electroscope is charged by conduction. Now, touch the electroscope with your hand. What do you notice? We find that the gold leaves collapse. The gold leaves.
Okay, I'll let you know why this is important as well, guys. As soon as you use your hands to touch this metal plate here, you'll notice that the gold leaves will start to lose its positive charges. Why? Because right now our hand detects that this metal plate is more positive charge, meaning to say, right, all the electrons from our hand, not all, some portion of electrons on our hand, right, all the negative charges are actually being conducted back into here, guys. And when it's being conducted back into here, yet again, it will become neutrally charged, right? It will become neutrally charged here. And then the whole leaf is going to drop back downwards, guys.
And what do you notice? We find that the gold leaves collapse. This indicates that electroscope is discharged. What happens to the charges? As you touch the metal disc, the electrons from the earth travels through the body and pass from the hand to the metal disc and neutralize the positive charges. We can also say that earthing takes place as we touch the electroscope. An electroscope can be negatively charged when a negatively charged ebonite rod is brought in contact with the metal disc. When it touches the metal disc, the gold leaves diverge due to the presence of similar charges on them.
Okay, so this here, what is happening here is that because there is excessive amounts of negative charge here, guys, what's going to happen is these negative charges, as soon as they touch, it's like a bridge for the electrons to start flowing into this metal plate already, you know. And because of that, these negative charges here, these will actually repel each other, and it will force more negative charges onto this metal plate here, and thus making it more negatively charged.
On them. As soon as we touch the metal disc, the negative charges flow to the ground, thus discharging the electroscope.
Okay, so yeah, if anyone's got any questions for that video or not, guys, anyone didn't understand any specific part or not from the video? So anyways, let me just explain it here once again, guys. There's two ways to induce charges onto this metal plate. The first one is charging by contact. Contact means to say you must touch it, right? You must touch it, meaning to say, today, if this thing was originally neutrally charged, right? When I bring a negative charge close to this plate here, what's going to happen is these negative charges are actually going to be repelled downwards as soon as they touch. And when they repel downwards as soon as they touch, they'll give them an excessive amount of negative charges, and thus they will start to repel each other, right? Alternatively, if I don't want to charge, I don't charge by contact, right? I can charge by induction. Induction means to say I don't touch them, but I'll bring the negative charge very, very close to the metal plates here. When I bring it very, very close to these metal plates here, right, what's going to happen is these positive charges will be attracted upwards, right, leaving some negative charges somewhere here, right? These negative charges will be somewhere around here. But as soon as I connect an earth wire here, what's going to happen is, right, the excessive amounts of negative charges that are concentrated here will be repelled down through the earth, right? Meaning to say, when all the electrons have been repelled, right, there is a lack or an absence of negative charges, right, then this thing here will yet again become positively charged. Yeah, if you look at the statements here, this is essentially everything that I've talked about, but in a more structured format, guys. This is an instrument for detecting and measuring static electricity, right? When a charge is put on the disc at the top, it spreads down. When there's a charge here, it will spread down to the plate and the leaf. This means that both the leaf and the plate will have the same charges. They will either become positive, positive, or negative, negative. The leaf can be made to fall again by touching the disc. When you touch the disc, you have earthed, this is a very important keyword, you have earthed the electroscope. When you earthed it, means to say it will become neutral again, guys, right? An earth terminal prevents the case from becoming live, so it will not have any excessive amounts of electric charges, right? Electroscopes can be charged in two ways. Number one, by contact. A rod is touched on the surface of the disc, and some of the charges is transferred to the electroscope, or it could be charged by induction. A charged rod is brought closer, it doesn't touch, it close to the disc only, then the electroscope is earthed and the rod is removed. Okay, guys, I will have to stop here this week, and because of that, you will not have homework. Say it, seriously. Guys, we'll continue this next week, guys, because we'll stop here today. I'll shut up. I'll reiterate this again next week before we go on to the exercises. Next week will be exercise week for these electric quantities. All right, guys. Yeah. If you have no questions, that will be it for today. But of course, if you have any questions, you're more than welcome to stay back to clarify anything that you don't understand.